This video explains the classical determination of internal forces on a single span beam. The span with the length L is loaded by the distributed load Q and the axial force F. How do we start when determining internal forces? First, we cut from left to right. This is the case of the positive side of the section. In this section, the shear force points downwards, the axial force points to the right, and the moment points counterclockwise. It is about the positive forces in the positive side of the section. In the negative side of the section, we cut the other way, from right to left. Here, however, the forces and the moment are opposite those of the positive side of the section. Now let's determine the shear force. First, we cut from left to right. In the fixed support, we have a vertical and a horizontal support force. Thus, the support in the horizontal direction fails because we only consider the vertical forces. An infinitesimal distance to the right of the support, the shear force points downwards. Now we add the sum of the vertical forces. It is important that we define the positive direction. It points downwards, like the z-coordinate. Due to the equilibrium condition, the sum of vertical forces must be equal to 0. This results in the shear force equal to as at the location x equal to 0. On the right, we are in the negative side of the section, so the shear force points upwards. The same applies to the support reaction Bz. For this reason, we now have a negative shear force at the location x equal to L. At the end of the span length, we have a negative shear force and a positive shear force at the start of the beam. In the case of a single span beam, where the resultant acts precisely in the center, the support forces have the same size and the same algebraic sign. Each support thus carries half of the resultant, or rather, QL2. Now let's draw the shear force distribution. The section is an infinitesimal distance to the right of the support, so there is no distributed load there. V of x equal to 0 is QL2. The same happens on the right. However, we are in the negative side of the section, so the shear force is QL2. In this way, we have the correct shear force distribution. Now we know the values on the left and right and can draw the linear distribution very precisely. In the case of constant distributed loads, the shear force distribution is linear. If concentrated loads are added, the distribution also shows jumps. You obtain the exact value of the jump by the section at the location of the concentrated load. We will determine the moment and axial force distribution in the next tutorial.